Hello, dear viewers. Welcome to TV Math Hub. This is your study pattern for competitive exams. Here you will find different questions, clear solutions, and the guidance you need to succeed. Subscribing is completely free. It is just your way of appreciating our work and supporting the channel. So don't forget to hit the subscribe button and let's learn together. Welcome to TV Math Hub. In our today's session, I will be taking you through fundamental concepts in real analysis and set theory. That is to say, infimum, supremum, maximum, and minimum of a set. These ideas are very crucial for understanding bounds in sets of numbers, and of course, they will always pop up everywhere from calculus to optimization problems. So, in this video, I will break it down step by step with clear definitions, explanations, and real examples. So make sure you stick around till the end of this exercise. So let us look at the definitions. So we shall first of all talk about what we call the maximum of a set. And we shall be saying the maximum of a set is the largest value in a set. And that value must be an element of a set itself. This is very important. The word is must, meaning that the maximum element must be one of the elements in the set. However, it should be the largest value or the largest element in that set. For example, let us take an example. If we are to look at a set, for example, S. So if you have a set S, which S here is consisting of elements, for example, 1, 2, 3, 4, 5, 6, 7. So these are the elements of the set. So you are looking for the maximum element. And we are saying that the maximum element must be an element of the set, meaning that the element must be one of these elements here, and that element must be the largest. So when you are to look at this, you realize that 7 is the largest element in this set. So 7 qualifies to be called the maximum of the set S. So what does it imply? It implies for an element to be a maximum, it implies that for an element to be a maximum, 1, it should be an element of the set. For example, let's say for an element M to be a maximum, it means this M must be an element of the set S. And for all the elements X picked from S, these elements here must be less or equal to M, meaning that M must be the largest. So for M to qualify to be called a maximum, M must be an element of the set, and for all other elements, they should be less or equal to M. When you look at 7, when you choose a member like 5, this 5 will be less than 7. When you choose a number like 6, this 6 will be less than 7. So for any number that you choose from this given set, you realize that it will always be less or equal to M. So that is what we call a maximum of a set. So having looked at the maximum of a set, let us now talk about the next definition. And the next definition will be about the minimum of a set. And likewise, we shall be saying the minimum of a set is simply the smallest value in a set, and this value must also be an element of the set itself. So we shall also use this given example. For example, out of these elements of the set S, which one is the smallest element? And there should also be a condition for it to be an element. One, all the elements of the set. If, for example, if M is a maximum, if M is a maximum of a set S, if M is, we are talking about a minimum, is a minimum of a set S, then first of all, this M should be an element of the set. And likewise, for all the elements you pick, from the set S, all these elements should be greater than or equal to m, meaning m should be the smallest. So all these elements should be greater or equal to m. So for that case, if we are to pick a smallest number here or a smallest element, that element should be 1. Otherwise, if you pick a number like 2, you will have, you cannot say that this 1 will be greater than 2. That one will not be possible. So 2 cannot be a minimum, because there will exist some number 1, which is a 1, for which this 1 here will be less than 2. And if that happens, then 2 cannot be a minimum. So for an element to be a minimum of a set, that element first of all must belong to the set. And after belonging to the set, that element should be, for all other elements, they should be greater or equal to m, that element. So for our case, if you are considering such a set, then it means the minimum of the set S will actually be a 1. So that is how we define a minimum of a set. We are saying it should be the smallest value in a set, for which it must be an element of the set itself. Otherwise, it cannot qualify. Then next we shall talk about the supremum, or what we shall be calling the sup of a set. The supremum of a set is the least upper bound of a set, meaning the set should be bounded. So if a set is bounded above, then the set will be having an upper bound. And if it has an upper bound, then it should have the least upper bound. Out of the upper bounds, what is the least value? And that is what we call the supremum. So in other words, we can say it is the smallest value that is greater than or equal to every element in the set. For here, there is no condition. It can or may not be an element of that given set. So we should be able to differentiate it from the maximum of a set. So what we are talking about the supremum is, we are saying that for the supremum of a set, so if, for example, you have an element, so you are having your set, which set is consisting of elements 1, 2, 3, 4, 5, 6, and 7, and we are to talk about the supremum, and we are saying it is the smallest number. It is the smallest number that is greater than or equal to every element in the set. So when you look at this set here, for example, which number is greater or equal to every element from this given set? So you realize that that number which is greater or equal to every element in this given set is actually 7. So the supremum for this set here will be 7. However, as we shall see in the coming examples, it is not a must that the supremum of a set has to be an element of the set. So it can be or may not be an element of the set. So long as it satisfies the condition that it is the smallest number that is greater than or equal to every element in the set. So we shall also distinguish it from the maximum by saying that for unlike the maximum, the maximum, the supremum, this sup here might not be an element, of the set, might not be an element in the set. So meaning that the supremum, that number which is greater or equal to elements of the set S, might be part of the set or may not be part of that set. We shall get to look at some different examples where that one is possible. And we shall also consider examples such as if you're having such set, you're having a set S for which you are taking X, and X is any real number that is between, for example, 0 and 1. So when you look at such numbers between 0 and 1, you realize that 1 is actually the number for which all other elements of this set are actually less than 1. So you realize that this set here does not contain 1. It does not contain 1, but 1 is the largest value for which all other elements of this set will not exceed. So all other elements of this set here will not exceed 1. For each number which is so long as less than 1, all those numbers cannot exceed 1. So it means that 1 becomes the supremum, but 1 is not an element of this set. So if you are considering all real numbers between 0 and 1, you realize that 1 will be the smallest number that is greater than or equal to every number in this set. Okay, so for that case, 1 qualifies to be called the supremum. However, 1 cannot be the maximum. So we shall keep looking at different examples, and up to the end of this video, you should be able to distinguish very well between the maximum, minimum, supremum, and the infimum. So that is about the supremum, and next we shall talk about so let's talk about the infimum, or what we call the inf. So this one here is the smallest value that is greater than or equal to every element. However, for the infimum, it is the greatest lower bound of a set. The greatest lower bound of a set, which means if a set is bounded below, then a set has a lower bound. But out of the lower bounds of that set, there is a greatest value, and that greatest value is what we shall be calling the infimum. So in other words, we shall be saying the infimum, or what we call the greatest lower bound of a set, it is the largest value that is less than or equal to every element in the set. So likewise, as we said for the supremum, the infimum can be an element of the set or might not be an element of the set. And when you consider such an example, actually the minimum will also become the infimum. When you look at this, we are saying that it is the greatest value for which all these elements here, that is the largest number for which all these elements here are less, actually all these numbers here are greater or equal to that number. So whenever you pick a number like 2, 2 will be greater than 1. 2 will be greater than 1. You realize that 3 will be greater than 1. You realize 5 will be greater than 1. So we shall be saying it is simply the largest number that is less than or equal to every element in this set. Meaning that for whichever number you pick in this set, 1 will always be less than or equal to each of these numbers, meaning all these numbers will be greater than what? Will be greater than 1. So 1 is the value for which all these numbers here are greater or equal to. So 1 qualifies to be called the infimum of this given set. And we have seen that actually the infimum of the set is actually the minimum of the set. And when you look at this, we saw it also is a supremum of the set, and also actually qualifying to be the maximum of the set. So we shall look at some of the key points on how we can distinguish under which conditions can we have the maximum as the supremum, under which conditions can we have the infimum as the minimum. So we shall look at all those key points such that we are able to distinguish the sets that have got the maximum, that have got the minimum, that have got no maximum, but they have got the supremum. So we shall look at those key points. So next, let us look at some of those key points. So what are the key relationships between the maximum, minimum, supremum, and the infimum? So we shall say, if a set has a maximum, its maximum is actually its supremum. And that is one of the examples that we have been looking at. You realize that this set here has a maximum, which is 7. And this maximum is at the same time qualifying to be called the supremum. So you realize such a set, if a set, so long as a set has got a maximum, then automatically that maximum becomes its supremum. However, the vice versa is not true. Not every set that has got a supremum has a maximum. Next, we shall talk about the next relationship, and we shall say if a set has a minimum, then its minimum is its infimum. That is one of the examples we have seen. This set here has got a minimum which is 1, but at the same time we are saying actually this is also infimum. So if so long as the set has a minimum, then that minimum will qualify to be called the infimum. So next, we shall look at a set can have a supremum even if it does not have a maximum. For example, if you consider the set of all numbers less than 1 has a supremum of 1 but not maximum. So we are talking about a set that has got, all numbers less than 1. So what are those numbers less than 1? So numbers less than 1 are very many. If you are having a set, for example, you are looking at real numbers, so where x is an element from a set of real numbers, and you are looking at the set consisting of such numbers, this set S is consisting of a lot of numbers. Numbers less than 1, you can begin with 0.999, all those numbers there. So all numbers that are less than 1 qualifies to be within this set. So there are very many numbers starting from slightly below 1. So all those numbers there qualify to be in this set. But these numbers here don't contain a 1. 1 is not part of this set. 1 is not part of this set. And as we looked at the definitions, we said that the maximum and minimum must be elements of the set. However much these elements here don't exceed 1, but 1 is not an element of this set. So if it is not an element of this set, then 1 cannot be a maximum. 1 cannot be a maximum. So in other words, this set here has got no maximum. This set has no maximum. But the set has got a supremum, and that supremum is 1, because all the elements that will be in this set here cannot exceed 1, and you cannot get any other number for which the elements will be less or equal to that number. Whichever number you think about which is less than 1, there will be an element that is greater than that number. You can think about 0.9999, but this cannot be the supremum, or you cannot say that all other numbers will be less than or equal to this. So then what about a number like 0.99991? Such a number will exist. So that's why we say that all the other numbers cannot exceed 1. So if they cannot exceed 1, then it means 1 qualifies to be called a supremum, though it is not an element of the set S. So that is one of the key relationship between the maximum and the supremum. So we are saying a set can have a supremum even if it does not have a maximum. And we can take an example of this. You realize 1 is not an element of this set. However, 1 qualifies to be called a supremum because all other elements here will actually be less than or equal to 1. So there is no any other number that will exceed 1. So 1 becomes the supremum. But 1 cannot be the maximum because 1 is not an element of this set. And whichever number that is less than 1 you think about, there will be a number that is greater than that number. And for that case, that's why we cannot say there is a maximum within this set. So next, the next relationship that we shall talk about is a set can have an infimum even if it does not have a minimum. That is almost related to what we have done here. So a set can have an infimum even if it does not have a minimum. For example, the set of all positive real numbers has an infimum of 0, but no minimum. If you consider positive real numbers, so any number that is greater than 0. So for example, if you are considering your set S, so set S is consisting of X, and we are saying X is any number that is greater than 0. So positive real numbers, all numbers that are greater than 0 are positive. And you are saying your X is a real number. So such numbers here, you realize that 0 will actually become the smallest value. All other numbers will be greater than 0. But 0 is not part of this set here. We are considering numbers starting from numbers that are above 0. So 0 cannot be an element of this set. So 0 cannot be 0 cannot be a minimum. 0 cannot be a minimum. And even if you say maybe I'm taking a number like 0.0001, that all other numbers will be greater than this number, then what about a number that will be like 0.0001? Such a number will also exist. So you cannot say that 0.0001 is the stopping point where all other numbers that are greater than 0 will be greater than or equal to this number. So that one will not be true, because there will exist a number like this which is actually less than that. So this, we cannot say that this set here has a minimum. There won't be we shall not have a minimum, but we shall have an infimum, because an infimum can be part of the set or may not be part of the set, so long as that is the value for which all other numbers are greater or equal to such a number, and that is only 0, for which all the positive numbers are actually greater or equal to that number. It is only 0 where all other positive numbers will be greater than 0. But other than that, you cannot have any other value. So that's why 0 is called the infimum, but 0 cannot be the minimum, because 0 is not part of the what? Part of this set. So that is about the key relationships, and lastly, we shall be saying that for finite sets, the supremum and infimum are the same as the maximum and minimum respectively, because they will always be elements of the set. So that is one of the examples that we did here. This is a finite set. This set here has got finite number of elements. So for any finite set, there will always, the supremum will always be the maximum, and the minimum will always be the infimum. So that's why for this set we said the minimum is the infimum, and at the same time the supremum, the maximum is the supremum. So for a finite set, that one is okay. So for a finite set, the supremum and infimum are the same as the maximum and the minimum respectively, because they will always be elements of the set. Okay, so that is about the key relationships, and after that we shall look at some few examples. Where we need to obtain the minimum, maximum, supremum, and the infimum. For example, we have this set. This is one of the finite sets, and I am sure at the moment you should be able to easily get the maximum. It should be easy to get the minimum. It should be easy to get the infimum, and it should be easy to get the supremum of this set. First of all, we have to check whether this set has got finite elements, and it is true, it has got finite elements. We can list them 1, 2, 3, and 5, the smallest being 1 and the largest being 5. So for that case, this is a closed bounded set of integers, and we can easily note the largest element, which is actually 5, the smallest element, which is in S, which is 1. 1 is an element in S, so it qualifies to be a minimum. Infimum, so we already have the maximum. So long as you have the maximum, then your maximum will become the supremum, and your minimum will become the infimum. So infimum, all other elements in this set are greater or equal to 1. So 1 will be the infimum, and the supremum, all these elements here are less or equal to 5. And for that case, 5 qualifies. So for this being a finite set, you realize the maximum is the supremum, the minimum is the infimum. So that is about that set, and I hope it is clear to all of us. So looking at another example, we are saying we want to consider this set here. This set here is a closed set. This is a closed interval which includes endpoints. So meaning that 0 and 2 some are the elements are also part of this set here. So in other words, this set here S is a set for which if X is a real number and you are taking all the elements from 0 to 2. So this is how we can write it. So all elements from 0 to 2 are the elements of this set. So here it should be easy to note the minimum. The minimum, as we said, it should be an element of this set. Since it is included, since 0 is included in this set here, so 0 qualifies because it is an element in S. 2 qualifies to be the maximum because all the elements from 0 to 2, and 2 is included with a 0, it means 2 is the biggest value or the largest number, and already is in the set S, and for that case it qualifies to be called the maximum. The supremum, all the elements that you will list in this set here will be less or equal to 2. So the supremum will be 2, then the infimum will be 0 because all the elements you will list in this set here will be greater or equal to 0. So 0 qualifies to be the infimum of the set. So from that, we shall be able to answer question 2. So question number 3 is having S, which is 0 to 2. There, you should note the difference between these brackets. These are open brackets, these are closed brackets. These mean that 0 and 2, all the endpoints, are included in the set. But for this, it means that 0 and 2 are not part of the set. So in case X is our real number, and this set here will consist of elements from 0 to 2, but 2 and 0 are not part of the set. 2 and 0 are not part of the set. So this is an open interval. This is an open interval, and this one here is a closed interval. So you should be able to note the difference between these two. This is a closed interval, this is an open interval. So if X is any real number, then X cannot be 0 and X cannot be 2. And for that case, when you are to think about the smallest number that is actually greater than 0 in this set here to be the minimum, then that number will not be there. So there is no number which is the smallest and it is not a 0 because 0 is not part of this set. So any number you think about will actually not become the smallest in this case. So whichever number you think about, maybe you think about 0.0001, maybe is the smallest. There will exist a number like 0.000001, which is also the smallest. So you cannot say there exists a smallest number. So we cannot have a smallest number. So the smallest number is not there. What about the maximum number? The maximum number, because 2 is not an element of the set, the maximum number cannot also exist. Because you cannot say a number like 1.9999 is the biggest number. So when you think about this, there will be a number which actually is this. So you cannot say that 1.9999 is whichever number you think about, there will be a number that is greater than that number. So we cannot have a maximum because 2 and 0 are not part of this set. And that is why we cannot have the maximum and minimum. However, all the numbers you think about cannot go beyond 1. They cannot go beyond 0. So for that case, 0 qualifies to be infimum. 0 qualifies to be infimum. For any number you think about, that number will be greater than or equal to 0. Will be greater than or equal to 0. So for that case, 0 qualifies to be infimum, and 2 qualifies to be the supremum. Because for each number you think about in this set here, that number cannot exceed 2. 2 will always be the number for which all these elements in this set here will be less or equal to 2. And if that is true, then it qualifies to be the supremum. So for such a set S as 0 and 2, we can see that this set here has got no maximum and no minimum, but it has the supremum and the infimum. So the next question to everyone is, what about such a set? So if you are having a set S, which set S here is consisting of 0 but not 2, what is the minimum, what is the maximum, what is the supremum, and what is the infimum? Remember that the maximum, minimum must be elements of the set. If you have a set, this is 4. If you have a set, for example, 0 and 2, what do you think about such a set? Please put it in the comment section. Try it. Tell me the maximum, minimum, supremum, and infimum of these sets here. So let us go on and look at something else, more of the examples. And the example next is they are saying consider the set A where x is an element from which where x is an element of real numbers, and we are saying that x or the elements of the set A are from 0 to 1, but you realize that this set here does not contain the endpoints 0 and 1, so which contains all real numbers strictly between 0 and 1. So these numbers are strictly between 0 and 1, meaning they are not part of the set. So we are saying that this set has no maximum because for any number in the set, you can always find a larger one. That is similar to what we have already so far talked about when we are talking about the set of this nature. So when we are talking about the set of this nature, you realize this is the same set. This is an open interval. This is an open interval. So likewise, the same knowledge should be applied to this. So for whichever value you think, you cannot say 1 is the maximum, because 1, first of all, is not an element of the set. So that disqualifies it to be the maximum. But whichever number that is less than 1 you think about, there will always be a number in the same set that will be greater than that number. So whichever number that you think about which is less than 1, then that number there will always exist another number which is larger than that. Okay, so for that case you cannot say a maximum exists. Then next we look at the minimum, and we shall say that for the case of the supremum of this set, the supremum is 1 because 1 is an upper bound and it is the smallest of all possible upper bounds. Whichever number you think about, maybe 2, 3, 4, all those numbers are upper bounds, but since they are upper bounds, 1 will always be the smallest. 1 is the smallest of all possible upper bounds. And also you can easily see that for all the elements from this given set, all elements that are between 0 and 1, all those elements will always be less or equal to 1. Because for it to qualify to be the least upper bound, first of all the elements must be, all the elements of the set, whichever element you pick here is less or equal to 1. So whichever element you pick out of this set will always be less or equal to 1. So that's why this one will qualify to be the least upper bound, or what we call the supremum. However much, this one is not an element of the set. So that is about the minimum and the maximum and the supremum. So next, this set has no minimum because for any number in the set, you can always find a smaller one. So we are saying 0 is not part of the set, so 0 cannot become the minimum. But in case you think about any other number which is above 0, for which is said to be the minimum, you will always find another smaller number. Even if you think about 0.0001, maybe that this is the minimum value, there will always exist a number like 0.000001, which is also greater than 0. So you realize that whichever number you think about, there will always be a smaller number. And for that case, we cannot say this is a minimum. We cannot say 0 is a minimum because first of all, 0 is not part of the set, so it is already out. But whichever other number you think about, there will always be a smaller number. So we cannot say this set has a minimum. So the set has no minimum. But this same set has got the infimum as 0 because this is the greatest lower bound, but 0 is not part of the set. And to make it easier for you, for whichever number you think that is within this set, that number will always be greater than or equal to 0. So there is no any other number. So for that case, 0 qualifies to be the greatest lower bound, because for all other numbers in this set, they will always be greater or equal to 0. And likewise, there are very many other great lower bounds, but 0 is the greatest because -1, -0.5, -2, all those ones qualify to be called lower bounds, but 0 will be the greatest of them. So all other numbers, like all other numbers which are less than 0, all other numbers which are less than 0 qualify to be called lower bounds. They qualify to be called lower bounds. But out of these numbers, 0 will be 0 will be the greatest. 0 will be the greatest number. So that's why we can say that 0 is actually the greatest lower bound, but 0 is not part of the set. So you should be now be in position to differentiate why we are saying 0 is an infimum, and yet we are not saying 0 is a minimum, because you can easily see that 0 is not part of that set. So that's why it is already disqualified to be a minimum. So that is about that example, and we can look at some few more examples, especially the increasing sequence. So if we have such a sequence S, which is given as this, so whenever you are given such a sequence, first interpret it by putting it in a form that you can easily realize. So when you have such, this is n is a natural number, so you begin with 1. So when you put n as 1, this becomes 1. 1 out of 1 plus 1. So you're having 1 out of 1 plus 1, which is 1 out of 2. So you realize your first element will be 1 out of 2. If n becomes 2, this becomes 2 out of 2 plus 1, which is the 3. So you realize you have a half. Next you have 2 out of 3. Next you put n as 3. N as 2, this becomes 2, this is 3, that is done. N as 3, this becomes 3 out of 3 plus 1, which is 4. N as 4, this becomes 4 out of 5, and this continues like that. However, we want to know whether this set here has a maximum, a minimum, then has a supremum and infimum. Now, for such a set, it is always better to put, not to just put these dashes. You need to know for any bigger value of n, where is the set tending to. For example, if I consider a number like 100, you realize the next term here, will be 100. For example, if n is 100, this will be 100 divided by 100 plus 1, which is 101. But if this continues, maybe it goes up to 100. If it goes up to n equaling maybe to 100,000, let's assume that. So this means we shall have 100,000, and this will be divided by 100,000 plus 1, that is 100,001. So you have such a number. So when you look at such a number, we are looking at where is this number, if n keeps on increasing, where does it tend to? So now everyone should be able to appreciate that if a number reaches, for example, if n is 100,000, you realize that this number will be becoming 0. If you divide this 99999, something like that. So this is 0.999, then again 99, and continue. So you realize that as n keeps on increasing, this value is tending to 1. So this is 0.9999. So the value keeps on, as n keeps on increasing, as n is becoming larger, then you realize that your sequence is tending to 1, though it might not exceed 1. So there is no point at no point where you will have a 1 here, but all the value is tending towards 1. As n is becoming larger, your s, or the terms of the sequence, are tending to 1. So what does this one mean? It means that this sequence, as it keeps on increasing, it is tending to 1. However, 1 cannot be an element in this set. The terms are tending to 1, but not reaching 1. Okay, so the terms are tending to 1, but they are not reaching 1. So for that case, it implies that our set is having a starting point here, but the ending point, it is only tending to 1, but 1 is not an element in the set. So that will help us now to define the maximum, the minimum, the supremum. So we are saying that the sequence is increasing and it is approaching 1, as we have seen, though 1 cannot be an element in this set. There is no point where you will have like a 4 divided by 4. However, all the elements will be coming closer to 1. So what next? It means that the maximum of the set cannot be reached. The maximum, we cannot have the maximum of the set, since we cannot have 1. This is tending to 1, but 1 is not an element in this set. So we cannot say there is a maximum. So whichever number you think about, there will be a number greater than that number. So this set has no maximum, but the supremum is 1, because all the terms of the set, all the terms of this set will surely be less than or equal to 1. So there is no way they can exceed 1. So 1 will become at the least upper bound. So supremum becomes 1. So for that case, you should now be in position to tell which one is the max, the minimum and the infimum. So the minimum value, of course, whichever value you think about, they cannot exceed half. You cannot have a number which is less than half. So half qualifies to be the minimum. Next, if half qualifies to be the minimum, then automatically the infimum will also become half. So long as the minimum or the maximum exists, then the supremum and infimum will exist. But that does not act vice versa. So the existence of supremum and infimum does not mean the maximum and minimum will exist. So for such a set, we can say that this one here is the infimum. At the same time, it qualifies to be the minimum, because the fact that it is part of the set, then it can be a minimum. Then 1, because this is approaching 1, 1 cannot be an element in this set, though 1 will become the supremum, because it will be the least upper bound. It will be the one of the upper bounds, but the least upper bound. Okay, so that is about this sequence. We can look at another sequence, possibly, so we can be in position to understand more about the supremum, maximum, infimum, and the minimum. So next, let us talk about such a decreasing sequence. And this is our sequence, s equaling to 1 upon n. And as I said, it is always better to know where the sequence is tending to. Having the dashes themselves does not guarantee that this one is going to infinity. So you need to first of all know the nature of the terms of your sequence. So when n is 1, we have 1 over 1, which is 1. When n is 2, we have 1 over 2. When n is 3, we have 1 over 3. So it means when n is 100, if n is 100, you have one of your terms as 1 over 100. When n is 100,000, so when n is 100,000, I will have 1 over 100,000. So I want to see the nature of the terms of this sequence by putting some other values of n that will give me the picture of how my terms are. So when you look at these terms, you realize they are decreasing. So this means that 1 is the biggest. So this is 0.5. So it keeps on decreasing. This becomes 0.01. Then this 1 divided by 100,000 becomes 0.00001. So you realize it is keeping on decreasing. But as it decreases, you realize it is coming to closer to 0, because this is 0.01, 0.00001, 0.00001. So you realize it is keeping decreasing, but it will decrease and it is coming closer. So this is tending to 0, because if this is 0.00, as you increase n now, if n keeps on increasing, then the terms will be tending towards a 0. So what does that one mean? They are tending towards 0 but cannot be 0. Okay, which means that the 0 can be your infimum. However, you cannot get the minimum of this set here. So you realize that 1 is the biggest value, so 1 can be the maximum. 1 qualifies to be the maximum. Then the supremum, of course, if this is already maximum, the supremum will exist. Then the minimum of this set here, you realize the minimum cannot exist, so the minimum is none. But the infimum will exist, because all these terms here cannot exceed surely 0. So these terms cannot be 0, because first of all, we are dealing with natural numbers. So under no circumstance where we shall have a negative value. So it means the infimum will be 0. So for all other terms will be greater or equal to 0. And 0 will be one of the lower bounds. and being one of the lower bounds, 1 will be the greatest out of the lower bounds. Think about all the numbers less than 0. Those will be lower bounds, but what is the greatest? The greatest will be 0. So for that case, the infimum will be 0. The minimum will be not there because we cannot have a 0 here. Though the number will be tending to 0, but 0 cannot be an element in this set. So for that case, that is what we shall get. Okay, so that is for a decreasing sequence. It is always better to have or to know where your sequence is approaching. So the sequence is decreasing and is approaching 0, and we can say the maximum is 1, which is obviously give us the supremum as 1, and then the minimum is not there, and the infimum is actually 0. So that is about such a sequence. So another example which I believe you can as well try out is this sequence here. You need to know where this sequence is approaching to. But by the fact that we can easily see from the first terms, you can easily see that the first term is 1 out of 2, the next is 4 out of 5, the next is, so this is increasing. This is an increasing sequence. So since it is increasing, then it means this will be the smallest value. So when you look at 4 divided by 5, that is 0. This is 0.5, this is 0.8, this is 0.9. So if your n becomes, for example, 10, then it means you will have a number like 100 over 100 plus 1. That is 101. So you realize that this is 100, this is 101, 9 out, this is 10. So you realize there is no point where you will get 10 out of 10. There is no point where you get like 1,000 out of 1,000. It is not possible. To be 1,000 means the upper one cannot be equal to this one here. So this one, the term here will always exceed this one by 1. So you realize that these terms here, if you pick a number like n equaling to 100, you put it, you realize that your values are becoming 2. Let us try n equaling to 100, so 100 squared. You realize the term when n is 100 will be 10,000. It will be 10,000 divided by 10,001. So you look at such a number. So when you divide such a number, you also get a number like 0.9999. So you realize that all these numbers, the terms here, as n is increasing, the terms are coming closer to 1. They are tending to 1. But 1 is not part of this set because there is no possibility of having a number like 10 out of 10. There is no possibility. So for that case, 1 cannot be reached. However, 1 will qualify to be the supremum, but 1 cannot be the maximum since it will not be part of that set. So likewise, it should be easier now to look at your minimum as 1 out of 2 and infimum to be also 1 out of 2 because this 1 out of 2 is already an element of this set. So for that case, 1 out of 2 will qualify to be called the minimum and at the same time the infimum. So that is basically about the infimum, minimum, maximum, and the supremum. So that will bring us to the end of our today's session. And please, if you find this video helpful, don't forget to subscribe to this channel. Of these numbers, check if there exists minimum, maximum, supremum, and infimum. So you will try some of these sets here. So if you have set S as -3, -1, 0, and 2, try and see if you are able to get those 4. 2, try a number where you have S equaling to, S is equal to 1 minus 1 over n, and n is an element from the set of natural numbers. And this is the second one. Then the third one, you can try to look at this set here, set S. Set S is consisting of numbers 1 and infinity. So try that one and see whether the maximum, the supremum, the infimum, and minimum exist. So try some of these answers here. You can put the answers in the comment. Yeah.